Hello, this is Miraj Patel, and today we're going to begin Unit 13, which is all about acids and bases. And so today we're going to be talking about properties of acids and bases, and talking about what is an acid, what is a base, and we're going to be talking about properties of them, common uses of them, neutralization reactions and salts, and then indicators. So that's what we're going to be talking about today. And so here we're first going to talk about what is an acid. And I'm sure most of you know, what acids are, and you think of them as like things that react. And acids do react, but specifically we're going to define it in terms of protons and how it donates or absorbs protons and stuff. And so acid is a chemical that dissociates in water to form hydronium ions. So this is a good term to know. So hydronium ions are H3O. So it's pretty much water with this extra hydrogen, or no, extra proton. And so that's a hydronium ion. And acids are proton donors. So here in this diagram, what would be the acid if we know that acids are proton donors? And that would be HCl here, because this HCl gave a proton to this water molecule, forming a hydronium ion and a chlorine molecule. And because this chlorine lost a proton, that's why it's slightly negative, and this oxygen gained a proton, and we write it as H plus because it's a hydrogen but without an electron, and that's why it's positive. So that's why these charges are there, but don't get too caught up with the charges. Just know acids donate a hydrogen, or a proton to a water and form hydronium ions, H3O plus. Then we have the opposite, which are bases, and bases are another chemical, and they're also very reactive. So not just acids are reactive, bases are also reactive too. And bases dissociate in water to form hydroxide ions. So in this case, bases are proton acceptors, so they take a proton instead of giving one. So here we have NH3, or ammonia, or ammonium, and so this ammonia molecule takes in this hydrogen from this water here, and it gets another proton, so it becomes positive, and then the water loses one proton, so it pretty much just has an extra electron with an oxygen and hydrogen, and that's why it's negative. And so remember, bases just take protons. So here we have a base, and because it took this proton and attached it to itself, that's why it's a base. And then we know that with bases and acids, so bases take protons, and acids give protons. So in this case, from knowing that acids give protons, this you can tell is an acid, or in this chemical formula example, because it gave away this hydrogen. So this is a acid. In this case, it acts as one, and this one acts as a base because it accepted it. And so now we're going to be talking about conjugate acid-base pairs. So here we have an acid, and it gave away a proton to this water, which is the base in this case. And so at the end of the reaction, we have chlorine here with the negative, and we have a water molecule with three hydrogens, or looking like three hydrogens. And so conjugate bases are formed when an acid donates a H. And so if you think about it, if we give away a hydrogen, now this chlorine has no hydrogen, so it's ready to take one back. So, and what do bases do? Bases are proton acceptors. So pretty much the acid, because it gave away its hydrogen to water, it wants to take it back because it's chlorine all by itself. And so because it wants to take it back, it's a base, but it's a conjugate base because it originally was an acid. And then we have the opposite, bases and conjugate acids. So here we have a base, and a base normally takes in a proton. So you can see here with this arrow, it took in the proton. And then at the end of the reaction, at the end of this reaction, we have a base here with three hydrogens and this one proton here. And then we have this water molecule with OH and just negative. And so because this base took a hydrogen, now it's ready to give it away, and acids, give away are proton donors. So conjugate acid is formed when a base accepts a hydrogen, and so because it's ready to give it away, it sort of turns into an acid, and it's a conjugate acid because it originally was a base. So just remember, bases and conjugate acids go together, while acids and conjugate bases go together. And always remember, just think about it in terms of protons. So if a base gains a proton, it's ready to give it away, so it turns into a conjugate acid. And same thing with acid. So an acid normally gives away protons, but once it loses it and once it accepts one, so it turns into a base, but it's a conjugate base because it originally was an acid. So just think about in terms of protons, and you'll understand this. And so a conjugate acid-base pair, you can tell or they're pairs because they're related by a loss or gain of one proton. So these two are a pair because the only difference between this one and this one is because they just gained NH4 plus just gained a proton. Otherwise, it would be NH3 if it lost that proton. So if they're related by a loss or gain of one proton, that means they're a pair. So this would be a base and conjugate or acid-base pair, conjugate acid-base pair. And then this one was H2O, but then it lost a proton and became OH negative. So because they're uh, they're only different by just one proton, this one's also a pair. So notice that the pairs have a very similar atomic chemical formula, because look, NH3, NH4, that's pretty similar. So so notice how, and also H2O and OH, they look very similar. They have both have an O and an H, but this one just has a 2, and then this one has a negative and without a 2. So conjugate acid-base pairs usually have a similar looking formula, so that's how you can tell whether it's acid or where it goes with. So you can just match it up by looking here to see that N was with this N because they only gained or lost a proton, so this one must be a pair, so the other two must be a pair. So that's how I would figure it out. And so here we have acids and bases, and here's some properties of acids and bases. So acids, if you think of lemon juice is an example of an acid, and what is special about lemons? They taste very sour. So remember acids with lemon juice and think of them as very sour. So like anything that tastes sour, like limes, tomatoes, oranges, like citric acid. So you see, like citrus fruit has acid in it, and that's what gives it sour taste. Then we have bases, which are opposite. So bases are pretty much like mostly cleaning products. And so if you ever like tasted soap accidentally, you know that it's very bitter. So just think of soap, and soap is a base. So because it tastes bitter, just remember soaps taste bitter, so bases are bitter. And then we have acids, on back to acids. So acids turn litmus paper red. So litmus paper is just an indicator. We'll talk more about that. And when we dip it in acids, it reacts with the paper and changes color, and it changes red. While bases, on the other hand, turn blue. So if we dip litmus paper into a base, it reacts and turns it blue. And both of them conduct electricity fairly well. And the cool thing about acids is that when they react with the metal, so we have a single replacement reaction, and remember types of reactions. So it's a single replacement because the zinc kicks out this hydrogen and forms an ionic bond or with zinc chloride, And then the single placement reaction with metals forms hydrogen gas. So acids, when they react with metals and do a single placement reaction, they form H2 gas. And see, notice how the zinc kicked out the hydrogen, and chlorine and zinc bonded and formed a ionic compound. And then hydrogen's all by itself and makes a gas. And the last thing is bases are very slippery. So think about how soap feels, and soap feels very slippery, so bases are slippery. So think of bases, just think of soap, and for acids, just think of like lemon juice and how it's sour. And so here's some common acids in probably in your household. And so acetic acid, uh, which is used for vinegar. Then there's carbonic acid, which is used in sodas. We have hydrochloric acid, which is used in your stomach. And then we have nitric acid, which is used as fertilizer. Ascorbic acid as vitamin C. And sulfuric acid as battery acid. So in batteries you find it. And what's one common thing about all their formulas? And it's pretty obvious. And you see that, notice that all of them have like an H in them. So notice how all acids have to have an H, and it makes sense because acids have to donate a hydrogen. So how can you donate something you don't have? Exactly, you can't. So all acids have to have an H, and usually the H is like by itself on the side, and or it could be bonded. But just remember, it has to have an H to be an acid. And then we have some common bases, and notice how we have a picture of a bunch of household cleaners. So most cleaners are bases, and some common bases are sodium hydroxide, which is used as drain cleaner in soap. Then magnesium hydroxide, antacid or laxative, which is used for like heartburn. So if we throw in a base to um, to ease your stomach of this acid. And then we have calcium hydroxide, and it's used for concrete and plaster. We have aluminum hydroxide, deodorant or antacid, and then we have ammonia, which is used as a cleaner. And notice how most of these have a OH in them, except ammonia. And notice how all their names have hydroxide, hydroxide, hydroxide. And so hydroxide just means this OH. So all their names usually have hydroxide, and they all usually have OH right next to each other, unless you have ammonia, which is weird. And so now we're going to be talking about neutralizations and salt. And so we have a example of a neutralization reaction, and neutralization reactions, all they are reactions when reactions of acids and bases that make salt and water. So neutralization reactions happen so they neutralize each other, and so there's no acidity or basis alkalineness of the product. So, and it always forms a salt and water. And so here we have an example of a neutralization reaction. So we have HCl and NaOH. So notice how, because this one has one hydrogen, it must be an acid, and you can also tell by looking at this one, it's OH. So what do we know about OHs? OHs are usually found in bases. So if this one's a base, this one has to be an acid, because acids and bases, they have to both be present in this neutralization reaction. So this base accepts this hydrogen, so this forms water, and then this chlorine and sodium meet together and form sodium chloride or table salt, and H2O is also formed, and that's hence this water. And so it does follow our simple rule: acids and bases, when they neutralize, they form salt, in this case NaCl, and water. And so here we have another example. So we're going to figure out which one's acid, base, and salt. So before I begin, I just noticed that KOH has a OH in it. So what does OH tell you about this? And did you say it's a base? And if you did, it is correct. So this one is a base. So by default, this one must be an acid if it's a neutralization, because we see we have H2O, so water, and KNO3 is a salt. So if we have a base and an acid, so, and this one's an acid, and you can tell because that's a hydrogen ready to donate. And so that one is an acid, so it donates that hydrogen. The other one, KOH, is a base, which accepts the hydrogen, or proton, I meant. And then KNO3 must be salt, because we know H2O is water, and water and salt is always produced. So if this is water, this must be salt. And remember, neutralization reactions neutralize the acid and base. So the product, there's no acid or base. So this is at pH of 7. And also a cool thing is that when we form a salt, salts are ionic compounds, and we know that ionic compounds, we balance the charges. So this is a neutral compound, and so is water. We know water is just neutral, it's in the middle. So at the end of a neutralization reaction, remember everything is neutral, so there's no acidity or basicity, so it's neutral. And so here's some salts, common salts. We have sodium chloride, which is table salt. Then we have sodium bicarbonate, which is used for glass. Potassium chloride, used as salt substitute to reduce sodium, because sodium chloride has sodium in it, so we use potassium chloride instead. And then we have potassium iodide, which used added to table salt for more iodine. Magnesium chloride is the salt that's used for roads, so now you know what that salt is. And calcium carbonate is used for chalk and marble. Then we have ammonium nitrate, which is used as fertilizers and cold packs. And notice how all these salts, they're ionic bonded, because they have a metal and a non-metal, and so these are all ionic and neutral. And then here we're going to finally talk about indicators. And an indicator, just like the definition says, is something that changes color, indicates something. So indicators change color in acid or base to indicate its pH. So here we have several examples. So I'm sure some of you have used litmus paper before, and litmus paper is a paper that changes color in acids or bases, and it turns red in acids and blue in bases. Then we have phenolphthalein, and phenolphthalein is a colorless liquid normally when it's in an acid, but as it gets to around a basic pH of 8, it starts to turn pink, and it turns very bright pink. And then we have red cabbage juice, which is pretty cool, because all you do is just literally grind a cabbage and make juice out of it, and there you go, you have an indicator. And so this indicator, it's normally pink. Red cabbage juices are usually pink, but then it can change to shades of green, or it could change into shades of like dark violet for bases and stuff. And then we have universal indicators, which are indicators that turns a separate color for each different pH. So the cool thing about this one is that each pH has its own color. So if you put this universal indicator in some liquid, it will change to the color of its pH, and you can tell exactly what pH it is. So here we have vinegar, club soda, and ammonia. And vinegar has a color of about maybe 3, so it's probably pH of 3. And club soda has an orangish color, so it's probably between maybe 4 and 5, because this one's a little lighter orange, but this one is too dark red, so it's probably closer to 5. Then we have ammonia, which is a darker blue, so it's probably a pH of 10. So universal indicators are special because they change color for every single pH, so you can tell the pH immediately when it reacts and changes the color, and it's very specific usually. And so here's a quick quiz to see what you learned about acids and bases. And so, question one, which of the following is a characteristic of bases? So let's go back to the slide so we can review all the characteristics. But before we review, let's just look at our answers. A tastes sour, B turns litmus paper red, C feels slippery, or D reacts with metals to form H2 gas. So let's go back. Okay, so here are the properties of acids and bases. And so acids taste sour, just think of lemon juice. They turn litmus paper red, they conduct electricity, and they form hydrogen gas when reacting with metals. So, and then we have bases here that have a bitter taste, turn litmus paper blue, conduct electricity pretty well, and last thing is that they feel slippery. So bases, just think of soap. So soap tastes bitter and feels slippery. And then for acids, think of lemon juice that tastes very sour. And so if we go back to our question here, what is a characteristic of a base? And so three of these are characteristic of an acid, and taste sour is definitely characteristic of an acid because think of lemon juice or citric acid. Oranges, lemons, limes, they all taste sour because of that citric acid inside. And then which of these changes litmus paper red? So bases, think of bases for litmus paper blue. So bases turn it blue. B and B. So bases turn it blue, so that's not characteristic. And then reacts to metals to form H2 gas. And if you remember on the slide that acids react with metals and they form hydrogen gas. So they are a property of acids. And if you think about it, if we poured, or if drain cleaner, which we pour down metal pipes, was in acid, it would react with all the pipes and corrode them and form hydrogen gas. So that wouldn't be a good thing. So sometimes you could use your like knowledge and what we've learned to apply it. So that's why bases aren't, used for drain cleaners and cleaning products because we often use it on metals and stuff. So that's why cleaning products are bases. And bases finally are feel slippery. So just think about that soap. Soap is very slippery. And also if bitter was on here, that would also be an answer of a characteristic of a base. And so, which compound is most likely to act as an acid and why? And so, is it H2O, NH3, NaOH, or H2SO4? And so, uh, remember, acids are proton donors, and remember, bases are proton acceptors, and the proton acceptors usually have an OH. So immediately you can see that C, NaOH is out. And so water is a special one because water can turn into both an acid and a base because it has two hydrogens, so it can give away one, and it can form OH. So that one's weird. So that one can go either way. So just ignore water for now. And then NH3 is ammonia, and ammonia is used as a cleaning product. So if it's used as a cleaning product, it's most likely a base, and in fact is. But it's weird how NH3 doesn't have OH, but it's still a base. And so even though we just eliminated like three answers, so the last one, H2SO4, can this be a base? And so it does sort of look like it, I mean, can it be an acid? Sorry. It can be an acid because it has two hydrogens and it could give away one. So the correct answer is H2SO4, and it's because it can donate a hydrogen or a proton to water to form, the acid hydronium ion. So it was H2SO4. And so when a neutralization takes place, one of the products is always carbon dioxide, a salt, sodium chloride, or a precipitate. And remember, when we have a neutralization reaction, the acid gives a hydrogen or proton to the base, and it forms water. And think of the ocean, a salt. So when we have a neutralization reaction, we always have water and a salt. So always remember water and salt. But in this case, sodium chloride is incorrect because it's not always NaCl. It just forms a salt. Like there's potassium iodide, potassium chloride. There's all sorts of salts that are out there. So it's not always sodium chloride. So it can be that, but it's not always. It's just a salt. Just know that. Salt is always formed. And so a blank changes color in an acid base. Precipitate, salt, ammonia solution, or indicator. So remember those pretty pictures with the bases and acids, the different pHs and colors, and those are called indicators. And the reason why they're called indicators is because they indicate pH based off of the color. So just remember, indicators indicate pH from the color. And so some examples are like phenolphthalein, litmus paper, and red cabbage juice. And then there's universal indicators that change color for every single pH. And so that is it for today. So today we talked about characteristics of acids and bases. Then we talked about conjugate acids and conjugate bases. So acid and conjugate bases are paired. And then we have bases and conjugate acids. And then we have, yeah, we talked about properties, and then we talked about neutralization reactions, salts, and then we talked about some indicators and what they do. And so I hope that helped you learn about all these following terms and important fundamentals of acids and bases. So on the next lesson, we're going to be calculating pH and some other stuff with acids and bases using some numbers, and I'm going to explain like what causes them to be an acid or base and like concentrations of hydronium ions. So we're going to have fun with that. And so I'll see you next time, and I hope you have a good day, and I hope this helped you.